Hi everyone. For today's video, I want to walk through the exercises in our textbook from chapter 4. Again, I'll be doing the odd numbered exercises, and we'll just walk through them. What we've been covering this week are measures of variability. That is, how in our data does it differ from each other? So let's start. The simplest measure of variability is the range, and the range of a variable is simply the maximum value minus the minimum value. So if we look at our first question here, A, calculate the range of the following sets of data, 4, 6, and 9. Thankfully they put these in order for us. The maximum value is 9, the minimum value is 4. 9 minus 4 equals 5. That's our range. Looking at B, B does not have them in order. 14, 17, 11, 19, 12. 11 is the lowest. The highest is 19. 19 minus 11 equals 8. These aren't that difficult. And because it's so easy to calculate, again, we don't really get a lot of usefulness out of the range. It's just a way of stating the difference between the maximum and the minimum. Let's take a look. Let's do E. E's got a lot of numbers here. We're looking for the minimum, so I'm just going to scan them real quickly. 66, anything lower than 66. 62 is lower than 66. Let's see if anything's lower than 62. No, so my minimum is 62. Looking for my maximum. Let's see, 91's pretty high. Anything higher than 91? Scrolling. Nope. 91 minus 62. Difference there is 29. So these are pretty easy to do. If you want, go ahead and hit pause and do C, D, and F. And I'll write the answers down and you can check your work. So hit pause. So the range for C, the answer there is 9, D was 12, and F was 2.55. Easy range. Let's go to number 3. 3 is going to ask us to calculate the interquartile range for each of the following sets of data. And again, the interquartile range, we have a distribution. The interquartile range is the middle 50%. So we need to find what is the 25th percentile and what is the 75th percentile. And then we're going to subtract those two. Your book gives the equation as, let's see, let me write it over here. Interquartile range n minus n to the 4th score minus n to the 4th plus 1 score. Okay, so let's do A. First thing we're going to do with A, I got to find n. So n is the number of observations. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 observations. So let's do our interquartile range for A. 8 minus 8 divided by 4 minus 8 divided by 4 plus 1. Okay. 8 divided by 4 is 2, and 8 minus 2 is 6. So I need the 6th score, and I'm going to subtract from that 6th score 8 divided by 4 is still 2 plus 1, the third score. So what I need to do is I actually need to order these. And looking at it real quickly, it's nice that it's actually been ordered for me. So the third score is 7, 4, 5, 6. The sixth score is 17. 17. Just want to drop this score thing down so as not to confuse you. Minus the third score, which is a 7. So the interquartile range is 10 for A. Let's do one more. Got room for one more here. Let's do an interesting one. Let's do E. E looks a little scary because of all these numbers. So first thing we do is count the number of observations in our data. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n equals 12. So let's use our equation. 12 minus 12 divided by 4 minus 12 divided by 4 plus 1 score. 12 divided by 4 is 3. 12 minus 3 is 9. So I need the ninth score. And I need to subtract from that. The 12 divided, again, sorry. 12 divided by 4 is still 3, plus 1 is the fourth score. Okay. Now, looking at this, E, they haven't ordered them, so I've got to go through and actually order these. I've got 4, 5, 340, 390. Okay, so I'm going to start, looks like my lowest one is 340. Any more 300s? I've got a 390. Okay. Next is the 400s. I'm just scanning these real quick. I got a 450, a 420, and a 480. So I'll go 420, 450, 480. Got those three. Okay. And now for the 500s, I've got a 560, a 510, a 560, and a 510, and a 540. So I've got lots of 500s. 540. Sorry, that should have been 510. 510. That's one of them. Second 510. 540. And then I got two 560s. Last two digits is a 670 and a 720. Okay, so there's my 12 numbers written out in order. I need the fourth score, 5, 6, 7, 8, 9, and the ninth score, 560 minus 450 equals 110. So my interquartile range for E is 110. Okay. So if you want, hit pause, work on B, C, D, and F. And when you hit unpause, I will write the answers down so that you can check. Okay. So that's interquartile range. We like it because it's less dependent on the outliers that the range is. But again, you're still only using two variables from your two observations from your data set. Okay. Not really sure what's going on with my slideshow here, so I'm going to end the show and discard all my ink and start back up again. Sorry for that. Question 5. For each of the following sets of data, we have 3 parts here. 1. Calculate the mean of the scores as x bar. 2. Calculate the deviation of each score from the mean. I can do that. That's subtraction. And 3. Check to see if the sum of the deviations equals 0. Well, I know that it's going to, as long as my math is correct. So this has got multiple steps. Let's just pick the hardest one and go ahead and do the hardest one first. Okay, so the first thing I have to do is to calculate the mean of the scores. The mean is equal to the sum of all the x's divided by n. So let's figure out the n first. 1, 2, 3, 4, 5, 6, 7, 8, 9 observations. N equals 9. Next, I need the sum of these observations. I'm just going to pull out my calculator. And I'm going to type 3 plus 8 plus 14 plus 11 plus 16 plus 7 plus 14 plus 15 plus 11. It equals 99. So x bar equals 99 divided by 9 equals 11. Okay, so the mean of the scores, x bar, is 11. 2. Calculate the deviation of each score from the mean, which is x minus x bar. Okay, well, let's do that. So I have a column of x's, I have my x bar, and then I need to calculate x minus x bar. Not a problem. My x's are 3, 8, 14, 11, 16, 7, 14, 15, and 11. 3 minus 11 is a negative 8. 8 minus 11 is a negative 3. 14 minus 11 is a positive 3. Notice I went ahead and put the positive there. It might be a good idea to go ahead and put that positive, so that way you can keep track. 11 minus 11 is 0. 16 minus 11 is 5. 7 minus 11 is 4. 14 minus 11 is 3. 15 minus 11 again is 4. 11 minus 11 is 0. Okay, now I need to, so there we go, I've calculated that. Check to see if the sum of the deviations equals 0. I'm going to do this scrolling down. A negative 8 and a negative 3, that's a negative 11. Plus 3 is 8. Plus 5 is, sorry, negative 8. Plus 5 is a negative 3. Plus 4 is a positive 1. Plus 3 is a positive 4. Plus 4 is a positive 8. Plus 0 is a positive 8. Wait a minute. I must have made a mistake somewhere, didn't I? Actually, yeah, I did that on purpose. Because what I want to show you is that very simple math is often the mistakes that we make in statistics. It's not that the equation itself is complicated, it's that sometimes you write down the wrong number. So 7 minus 11 was not positive 4, it was negative 4. So I'm just going to double check my work, because I've already made one dumb mistake. 3 minus 11, yep, that's a negative. 8 minus 11, that's a negative. 14 minus 11, that should stay positive. 0. let's see, 16 minus 11 is plus 5. Yep. 7 minus 11 is a negative 4. 14 minus 11 is a positive 3, positive 4. Now let's do this again. 8 minus 3 is negative 11. Plus 3 is a negative 8. Plus 0 is still a negative 8. Plus 5 is a negative 3. Minus 4 is a negative 7. Negative 7 plus 3 is a negative 4. A negative 4 plus 4 is a 0. A 0 plus a 0 is still a 0. There. Once you do your math right, you get the right answer. So pick another one of these. Pick an easy one. And you should be able to get the same proof. 2 and 4 and 6. That's the easiest one. The average, well, I know the average is 4. I can tell just by looking at it. Because 2 is 2 less than 4, and 6 is 2 more than 4. So my average is 4. I'm going to get a negative 2, a 0, and a positive 2, and the sum of those are going to equal 0. There you go. What we're trying to show here is why we're going to square when we do the deviation, standard deviation, and the variance. So here's question number 7. For each of the sets in the data in exercise 5, calculate the variance. This is asking you to use the definitional formula and the computational formula. The textbook likes to do this, and so I'll write these both out for you. We're going to do s squared as, we'll do the definitional one first. This is in page, the equations are listed in page 128 of your textbook. So the variance, s squared using the definitional formula, s squared equals the sum of x minus x bar squared divided by n minus 1. The computational formula is s squared equals the sum of x squared minus the sum of x divided by n . This one's a lot messier, and this is why it's a lot messier. The computational formula, the big difference there is the fact that they explode out this sum, this x bar right here. They make this the equation for the average. And you can kind of see that right here, right? Where it tells you to take the sum of x squared. It's taken this square and deposited it with that x. And then subtract from it the sum of x divided by n. This is a lot messier. I really don't think you guys should be using this. I think instead what you should focus on is doing bucket on the floor. And so if it requires you to use an equation, go ahead and a second equation, go ahead and just calculate that first. So go ahead and calculate x bar first and then just plug it in, rather than trying to do all of this in one step. This is too much. It's not necessary. So even though the book gives them to you, my advice is don't. Just don't do it. Okay? But maybe for this example I'll go ahead and do it just to show you why the definitional formulas are probably quicker. So let's use a new one. Let's use B. 5, 6, and 13. So here's my data. I gotta have the sum. Okay. So 5, 6, 13. I have to do the summation, so that's my x's, so I need x bar. What is the average of 5, 6, and 13? I'm just going to plug that into my calculator. 5 plus 6 plus 13 That equals 24 divided by 3, because I have 3 numbers. X bar is 8. X minus X bar. Now I'm doing this part of the equation. 5 minus 8 is negative 3. 6 minus 8 is negative 2. 13 minus 8 is a positive 5. Now I'm going to square it. X minus X bar squared. Negative 3 times negative 3 is a positive 9. 2 times 2 is 4. 5 times 5 is 25. So I've done this part here of my equation. Now I just need to sum it up. So 9 plus 4 is 13, plus 25 is 38. S squared equals 38 divided by n minus 1. My n is the number of observations in my data set. I had 3 observations. Minus 1 is 2. 38 divided by 2 is 19. I'm going to double check, make sure I got this right. Take a look at my math. 9 and 4 is 13, and 25 is 38. So my S squared is 19. Correct. There we go. Let's take a look at how the equation in the computational formula would work. I've got my sum of x squared minus my sum of x divided by n squared. Okay, so let's work this through and make sure I've got my numbers correct. So let's do another column here. My sum of x squared. Let's focus on this first part. Sum of x squared. So I've got to do an x squared. 5 squared is 25. 6 squared is 36. And 13 squared is, I don't know off the top of my head, so I'm going to do 13 times 13 in my calculator and get 169. So that's what x squared is. Now I have to sum it. 25 plus 36 plus 169 equals 230. So I've got my sum of x squared, that is 230. N minus 1, let's do that one real quick. N minus 1, n was 3, because I had 3 observations, minus 1, so that's going to be 2. Now the next thing I need is this here, the sum of x squared divided by n. Inside the parentheses, it has the sum of x. So that is not the sum of x squared, like we just did in the first part. It is the sum of x over here. So let's do the sum there. 5 plus 6 is 11, plus 13, that's 24. So now I need 24 squared divided by n. N, remember, was 3. 24 squared is actually, I'm erasing to save space, 576. Before I can subtract that, I've got to do 576 divided by 3. Again, I'm erasing to save space. That's 192. Got room here. S squared 230 minus 192, I hope it's 38, divided by 2 is 19. I'm thinking that's not as easy. I'm thinking there's more potential to misunderstand what you need to do in the order of operations. So that's why I tend to like the definitional formulas better. Again, bucket on the floor. Calculating a mean, that's a very simple task that you can do repeatedly. Just go ahead and calculate it. With the computational formula, there's more of a chance to make a mistake. So personally, again, I advise you, go ahead and use the definitional formulas. I'm going to not test you on a lot of these computational formulas. I try to maybe do it a little bit, but really what I want you to understand is that the computational formula is just taking the steps for computing a different equation and incorporating them into the equation of interest. And since we have a little bit of math phobia, I don't want to make the equations look scarier. I'd rather you do 3 equations that are simple than one big equation that looks scary. I'm going to go ahead and let you hit pause, and I'll write down the answers for the remaining ones that we didn't do. So go ahead and do that. Hit pause. Okay. So there's all of our answers. So number 9, using the same sets of data, for each of the sets of data in exercise 5, calculate the standard deviation, that's S, and the population standard deviation. For each data set, which is larger, the standard deviation or the population standard deviation? Okay, let's start from scratch here, and let's pick one that we haven't used before. Let's do D. D's not so hard. We're going to start with D. Okay, so for the standard deviation, that's just the square root of the variance. Our standard deviation, again, we're going to use the easier equation. So I'll go ahead and just write that down. We're going to use So what do we need to start solving for D? How many observations do I have? N equals 1, 2, 3, 4, 5. Okay, so now I have my N. I still need to do my X minus X bar. 5, 2, 7, 13, and 11. That's my X. My X bar is, well, I need to find the average. Okay, so over to the side here, let's do our sum of X. Turn on the calculator because I'm being lazy. 5 plus 2 plus 7 plus 13 plus 11. That's 38. So the sum of X is equal to 38. 38 divided by 5 is 7.6. Now if I do X minus X bar, I've got a decimal point here. So it's going to look a little bit more complicated, but 5 minus 7.6 equals a negative 2.6. 2 minus 7.6 is equal to a negative 5. 0.6. 7 minus 7.6 is negative 0.6. Now we're into the positive number. 13 minus 7.6 is 5.4. And last but not least, 11 minus 7.6 is 3.4. Now I'm going to quickly just check to make sure that these zero out. So I've got my calculator again, and I'm going to do 5.4 plus 3.4 minus 0.6 minus 5.6 minus 2.6. And my calculator says 0, so that's great. So the sum of all of those is 0. My math is correct. The next thing is to square them. Squaring's great because it takes away the negative sign. 2.6 times 2.6, according to my calculator, 6.76. 5.6 times 5.6 is 31.36. 0.6 times 0.6 is 0.36. 5.4 times 5.4, 29.16. And the last but not least, 3.4 squared is 11.56. I only use 2 decimal places. It's called significant figures. One of those little tiny details you learned in school. In statistics, we pretty much go out 2. So if you have an answer, all of these came out exactly into hundredths, but if you have an answer that goes into the thousands, be sure to round up to the nearest hundredths. Next step, I need the sum of all these. So I'm going to type them in my calculator. The sum is 79.2. Okay. I think I'm ready for my equation. So my sum of x minus x bar squared is 79.2 divided by n minus 1, so 5 minus 1 is 4. .2 divided by 4 in my calculator is 19.8. This is the part where you turn your phone sideways, or if you're me, you look for the little check mark button on your calculator. It's 4.4497. So I'm going to take this, and like I said, I'm going to round it up to 4.45. So that's my standard deviation. I'm going to grab my textbook here and double check and make sure I got the right answer. So 9D, yep, S equals 4.45. Got it. Sometimes the calculator helps. Okay. So the next question is, for each data set, which is large, and the population standard deviation. I didn't go over this in class. I hinted at it. The only difference between the standard deviation for a sample, which is S, and the population standard deviation, which is sigma, is this degree of freedom that we're collecting here, because we're using a sample. When we have the population, we don't have to subtract 1. So if I take this part of it out and change my equation, okay, I take away that negative 1, Don't forget that I did that. So now my 79.2 is divided by 5. 79.2 divided by 5 in the calculator equals the square root of 15.84. So I'll do that. I'll do the square root, find my check mark button. 15.84 equals 3.9799, and of course that's going to round up to 3.98. The question is, for each data set, which is larger, the standard deviation or the population standard deviation? Well, for this data set, and spoiler alert, for all of them, when you have a smaller denominator, because of the subtracting of the -1, you're always going to end up with a larger, in the end result, a larger standard deviation. The reason for that is we want to be, when we're using a sample, a little bit more tolerant. We want to have more variance than there might actually be in the population. So that's why we do the -1. Okay. That's question 9. Let's do 11. 11 actually is using some real data here. One study stated the research hypothesis: violence behavior in children may be reduced by teaching them conflict resolution skills. The variable violent behavior was measured by the number of fights in which each student was involved. Below is a frequency distribution table for the number of fights for 12 students. So what do we have here? Do we have the number of fights? Is that the independent variable or the dependent variable? Well, the theory is that this outcome of violent behavior, we want to reduce that by giving them conflict resolution skills. So increasing conflict resolution skills should decrease the number of fights. Our independent variable is the skills. Our dependent variable is the number of fights. I'm going to skip A, and let's just focus on B. Based on your value of the standard deviation, what is the average difference between the number of fights a student's got involved in and the mean? So A was just asking us to compute the standard deviation, but I needed the space on the slide. So let's go ahead and do that for this variable. Remember, our standard deviation is the square root of our equation for variance, which is the sum of x minus x bar squared divided by n minus 1. I'm still using, I have a sample here, right? I don't have every student in every school, so I'm still calculating the standard deviation of my sample. Now let's take a look at our sample for a second. The first thing we're going to calculate is our average, and we need the sum of x and we need the number of observations. So we have 12 observations. This again is a frequency distribution table. This makes it look like you only have 1, 2, 3, 4, 5 observations. But actually, when you look at the number of times that that value appears in the data set, we actually have 12 observations. So how to do this? Well, let's actually do it the traditional way. Here is our variable that we're interested in. For right now, I'm still going to label it x, even though it's a dependent variable and I should call it a y, but let's just leave it at x right now. One student got into 4 fights. 2 students got into 3 fights. 5 students got into 2 fights. 5. 1 student got into 1 fight, and 3 students got into 0 fights. Getting really small here because I've got 12 rows. X bar, I need to do the sum of all of our x's. Quick way to do that, f of x, frequency times x, 4, 2 times 3 is 6, 2 times 5 is 10, 1, 1, and 3 zeros. So let's add these up. I've got 4 plus 6 is 10, plus 10 is 20, 21, plus 0 is 21. So the sum of all of my x's is 21, and that's going to be divided by 12. 21 divided by 12, 1.75. Oh, I was thinking that was going to be a scarier number. Sometimes you get surprised. Do my difference, x minus x bar. Twelve rows. This is about our limit for how much we can fit on a slide. Now I need to x minus x bar now I need to square that. I'm getting some very long numbers here. So now we're at the point where we're going to introduce rounding error, but I don't care because we need to get these done. Alright, 1.25 squared is 1.5625. I'll leave it at that. 0.25 squared is 0.06. Oh, I found a mistake. I hope you guys caught that. I hope you caught that as you were working along with me. So 1 minus 0.75 is... Oh, I made a big mistake. Fortunately, it didn't quite matter. Okay. What mistake did I make? Well, I was doing... I had the wrong x bar in my head as I was jotting these down. I should have said it out loud. 2 minus 0.75 is a positive 0.25, and 1 minus 1.75 is a negative 0.75. And 0 minus 175 is a negative 175. Almost made a mistake. Good thing I was double checking as I was doing my work. So 0.75 squared is 0.5625, so I'll leave that off. And 1.75 squared is 3.0625. I'm going to leave that off. Dropped a lot of 0.25s, 0025s as I was doing this. Alright, now I need to sum these. I'm just going to go ahead and type it all in my calculator. 5.6 .06 plus, I'm actually going to do something a little cheating and use some parentheses here. I've got 2 times 1.56 close parentheses plus, in another parentheses I've got .06 times 5 close parentheses open parentheses, got 0.56, and I've got 3 times 3.06. The sum of all these is 18.22. So 18.22 divided by n minus 1, which is 11. Six, 5, 6, 3, so that actually rounds up to a 1.66. Now I'm going to clear my calculator and I'm going to do the square root of 1.66. And so S equals 1.29. Let's call it that. Alright, going to check in the book. S equals 1.29. All of that mess for one very simple number. Okay. Whew. So what is the average difference between the number of fights a student's got involved in and the mean? Our mean was, what was our mean again? 1.75. So the average difference was 1.29. Let's remind ourselves why that's important. Hopefully I don't regret erasing all of this. If I can actually get all this to erase. Okay, so remember we have a distribution in our data. Here it is. Our average was 1.75. And we had fights all the way from 0 to 4. And we know that 68%, because of the empirical rule, are going to fall between 1.75 and a half a fight. 1.75 minus 1.29. That's a 0.46, and 1.75 plus 1.29, that's 3.04. So most of our observations are going to be between half a fight, which again makes no sense, and 3.04. So the average distance away from the mean is 1 fight. You have to do some rounding a little bit. So I would say that comfortably, if you want to do some rounding, you could generalize by saying, well, the average student got into 2 fights, but the average difference from the mean was 1 fight. Okay. Oh my goodness, here we go. Now, here we have an example, a quiz given to 25 students, n equals 25. Each student's score on the quiz is the number of items answered correctly. The scores are listed below. There's a lot of quizzes here. 22, 15, 11, 9, 12. Oh boy. How would we do this? Okay. Well, we should do it the right way. We should do it old school. We should write down each individual number. it's not going to fit. I'm going to be so close. Oh, it did fit. So that's our x. Then we'll do x bar. Then we'll do x minus x bar. Hopefully you're doing this like on a fresh notebook paper. And then we're going to do x minus x bar squared. That's what we're going to do. So I'm going to challenge you. Go ahead. I dare you. Pause. And then when you come back, after you've gone through this, I'm going to give you the correct answers. And then you're going to tell me whether you got it right or not. Okay? So hit pause now. Work on this for about 5 minutes. Please use your calculators. And then in a second, hit unpause when you're done. Ready? Challenge accepted. Go. And you're back. So here's your answers for 13. S squared is 19.89 and S is 4.46. Remember, you're going to be close because of rounding and things like that, but that's what you should have gotten. I hope you did a good job and you didn't just chicken out like I did. All right, 15. Here's one of these create your own. So let's look at this. On your own, create 2 distributions of 10 scores that have the same mean but differ in their amount of variability. So I want the mean for group 1 to equal the mean for group 2. But the variability, so the variance of group 1 and group 2 should not be the same. Okay, well that's easy. First one, group of 10 scores. Let's just do an easy one. 1 plus 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's 10 numbers. If you add all these together, 1 plus 2 plus 3 plus 4, all the way through, that total is 55. Which means the average is 5.5. Because remember, I did 10 numbers. 55 divided by 10 is 5.5. Okay. Now, I need to create another group of 10 scores that have the same mean, but differ in their amount of variability. 10 scores, 5.5 is going to be their average, but the sum of the scores has to add up to 55. In my mind, I'm thinking, okay, 55 10 times is 5.5. I could just write 5.5 all the way across, but then it'd have 0 variability. So let's make it 5 and 6s. 5 plus 6 plus 5, 6, and then a 5 and a 6, and 5 and a 6. And one more group, 5 and a 6. So now I have 10 numbers. They're all 5s and 6s. And if you notice, what I've done is 5 plus 6, 5 plus 6, 5 plus 6, 5 plus 6, 5 plus 6. They add up to 11. I've got that 5 times. I've got 55. There we go. Now, are they going to have the same amount of variability? No, they're not. Because I already know how much this group of data here is going to vary from the mean. Because my mean of this group is still 5.5. What's going to be the average distance away for my group 2? Well, every single number here has the exact same difference. The standard deviation for this is going to be 0.5 because each one of those observations is going to be 0.5 away from the mean. There we go. Now, if I want to do B, B says create 2 distributions of 10 scores that have different means but have the same amount of variability. All right, well, let's call B here, we'll use 2 and 3. So for B, the variances need to be the same for groups B and C, sorry, standard deviation. But the means of B and the mean of C have to be different. Okay, well, I can do this. Easy. I just need the total to not be 55 when I add these 10 numbers together, but I still need the difference between the mean and those numbers to consistently be 0.05. So pick your favorite number. My favorite number, 4. Okay, so I'm going to create a data set where the average is 4. Again, I want the means to be different, but the variation from that is going to be 0.5. So here we go. 3.5, 4.5, 3.5, 4.5. I gotta do it one more time. There we go. My sum's going to equal 40 because I've got, again, an average around 4. And my variance is going to be the same because every single one of these is 0.5 away. There we go. So C, what does this imply about the information that is necessary to accurately describe a distribution of scores for a variable? It means you need both. Because again, as we've talked about this, in a distribution of variables, the mean tells us where the center point is, but the variance tells us the shape of the curve. You need both. Let's look at 17. What if someone told you there's a great deal of variability in the scores for my variable? From this statement, can you tell whether the shape of the distribution is symmetrical or skewed? Why or why not? Well, no, you can't. Because we have a distribution, and if there's a great deal of variability, what's going to happen to this? Well, our curve is going to be pushed down, and it's going to flatten as variability, either s or s squared, increases. That's what's going to happen. Variability away from the mean increases, it gets flatter. If not, which is no, we said no, what would you do to determine the symmetry of the distribution? Well, that's easy. We know this because we know that our measures of central tendency are what are important here. And what we really need to know are the mean, the median, and the mode. The mode tells us how many humps. The mean tells us the center, and the median tells us whether or not it's skewed. That's a chapter 3 thing. Okay, hopefully this makes sense. One more. An employment survey in 2009 was conducted to find the average starting salaries of people receiving PhDs in psychology. The mean starting salary for psychologists and assistant professor positions at universities was $60,000 with a standard deviation of $10,000. So we're going to call those profs. Profs had a mean of 60K and a standard deviation of 11K. Psychologists in their first year of practice also report a mean of approximately 60,000, but with a standard deviation of 16,000. Let's call those docs. They can prescribe drugs. Okay, their mean for the docs was still 60K, but their standard deviation was 16,000. A, which type of psychologist has more variability in income? Okay, we'll look at the two variabilities. Which one's bigger? The docs do, because they have 16K. That's their variability. It's bigger. For which type of psychologist could you more accurately predict a salary for, and why? Well, if we're trying to guess salaries, I would say the professors are easier to guess, because their distribution for profs is a lot tighter, remember the empirical rule, than the distribution for docs, which will be a lot wider, because their curve is flatter, and so there's a greater variability around or away from the mean. This is going to be important. Again, we have to have in our mind this notion of a distribution of a variable. And what we're going to do from now on is playing with these normal curves and figuring out the area under the curves and the shape, and whether the shape is the right shape, and make assumptions on that. And so I really hope at the end of this video you're sort of clear on what a variance is, whether it's computing range, interquartile range, variance, or the standard distribution, but also why that's important to understanding the shape of our data, because it's the variance that tells us whether the curve is tall and skinny or shorter and wider. And I really hope that's it, because man, that's a lot of questions. Yep, that's it. We're done. Thanks everybody. See you in class.